Let's pick up with this router lab and see where those packets are going wrong, because as we saw with that debug on router 3, they're definitely leaving the router. And let's just go ahead and quickly, in case it's been a while since you watched video 2, let's run that debug IP packet. I know, like a TV show where they show you something and then they go to a 3-minute commercial and they show you the same thing when you come back, which I think is what all of them do now. Anyway, we can see the packets are being sent. And there's no problem there, but the problem is, of course, they're not going through or getting that odd ping result of u.u.u. So what you do in this situation, whether it's a complex network or a 3-router network, is you start going downstream to see where the problem is, because the packets are leaving here. We just don't know what's going on with them downstream. So we could run a command called traceroute. And this will give you a hint as to what's going on. I left the debug running, and that's okay. We'll turn that off. I want to run the traceroute again, though. And we're seeing .1 twice. That's a pretty odd result. It's like they're going down to .1 and they're stopping right there. So that's kind of pointing where the problem is, even if we didn't already know. But let's run show IP route. And what you would do in this scenario is just look at this and just say, okay, what's the next hop for these packets? Well, there's only one matching route here for 2222, and that is the static route that has the next hop IP address of 172.12.123.1. So that kind of narrows it down for us as well. What are we going to find when we look at the routing table on router 1? We're going to find the connected route to serial 0, and that's it. So router 1's getting these packets as the hub of a hub and spoke network and then saying, what do you want from me? I don't have any kind of route that matches 2222 at all, so I'm just dropping the packets and I'm letting that router know that it didn't go through. So we start getting those unreachable messages. Well, we have a couple of options here, of course, when we're sticking to static routing. We could just create another static route to 2222 from here and make 172.12.123.2 the next hop IP address. We know how to do that, though. We've hammered those options. You know the IP route options cold, except for a default static route, because we haven't created one of those yet. So let's go ahead and do that now. And you still do it with the IP route command. A lot of the rules are still the same. The odd thing is, and it's just something you have to get used to when you're choosing it, say, on a multiple choice question in a practice exam, is that the mask and the network are all zeros. So it looks a little funny. So this is a legal command. Now, let's look at our next choices. They're the same kind of choices we had with the regular static route that we created before. We could put the forwarding router's address, the next hop IP address, or the local exit interface. And again, we're going to use the next hop IP address here, and that would be 172.12.123.2. And that's it. So now that we've done that, let's take a look at the routing table. And a couple of big differences here. First off, we have a gateway of last resort. I don't think we've had one up to this point. And we've got it's 172.12.123.2 to network all zeros. So right away, even before we get to the individual route entries, we're being told, hey, if we get packets and we don't know what to do with them, we're sending them down to 172.12.123.2, and we're going to let that guy sort it all out. Then you have a static route to all zeros with the zero mask, and we kind of expect this, and there's 172.12.123.2, but notice that there's an asterisk here with that S. The asterisk is a candidate default route, and in this case, since we only have one possible default route to even be a candidate, that's the one we're going to use. But what you'll find, and actually I'll show you one of these in the OSPF section, there are other ways to get default routes generated than writing your own, and they can come in handy, but if we have two default routes, obviously we got to pick one. And that's why you see the interesting term candidate default instead of just default. So let's see if we can ping 2222 first off from here. And there's no problem at all. It comes right back immediately. So if we can ping router 2 from here, router 2's loopback from here, that is, we can probably ping it from router 3, and success. And let's run debug IP packet and send that ping one more time. And you can see now, here's the packet source 123.3, the local router, destination 2222, etc. And you get 5 of those and flipped around for the reply packets to come back. And that's it. So that particular lab gets us to look at a couple of different types of static routes. We saw a regular static route, then we saw a default one. And as I mentioned, if you create an address or a route to a particular host, then one host and one host only, that's what we call a host route. And that is not what we put in here, right? Because it's 2220. Okay, so that gives us a look at a couple of different static routes. Let's see something else here on the board. And these are from the study guide. If you pick one of those up, it's going to show you that the pings were going to 2222, but then stopped because there was no route for 2222. So we created a default static route. Again, the syntax for that's a little funny looking. All zeros for the network, all zeros for the mask, and then, as usual, the next hop IP address or local router exit interface. And once we did that, we took care of it because the pings went right through and they came right back. So let's talk about another way or another use for static routes that I want to mention here, because they can help you cut back on unnecessary overhead. Necessary overhead we need to keep, but unnecessary overhead we can get rid of. And this is a scenario that you run into more often than you'd think in today's production networks, because again, I've worked on networks where there were 20 spokes and one giant hub router or 2 hub routers doing the job. Well, in this network, all roads lead back to the hub. If any spoke wants to communicate with any other spoke, what is the next hop? It's always going to be the hub router. As a matter of fact, anything these spokes want to send, period, is going to be, the next hop's always going to be the hub. Well, in this case, let's say that you had 10 networks on each one of these spoke routers. So if we were running a dynamic routing protocol, then each router would be learning 50 dynamic routes. Then the next hop IP address for every one of those single networks is going to be the hub. So there's no use in having a routing table that big. What I always say, you want to have a routing table that's clear and concise. Complete and concise, because it's got to be complete, of course. If we can't get where we want to go, keeping it concise is not doing us any good. But you want to keep it as small as possible because the routing process takes time. And the bigger your routing table, it takes a little bit longer every single time because the router is always looking for the best match. It's not like an ACL, which you'll see later in the course, where you start at the top and as soon as you find any match, you just stop. It's going to look through the entire routing table for the best match. So that's a lot of work. And some of these spoke routers, and I know that I am speaking absolute blasphemy here, but sometimes you're going to have to work with routers that are not the latest and the greatest and the most powerful. I know, it's a shock. But some people in some books out there just pretend like every router you ever work with is going to be the latest and the greatest, and it's going to be plenty powerful, and it's going to have the latest IOLs, and it's not. So if these spoke routers are, shall we say, not the most powerful routers in the universe, you don't want them to have all that overhead, because there is overhead involved, of course, with keeping a dynamic routing protocol. You got to have some kind of routing update or keep alive or something in there, where static routes don't have that. So this is a scenario where I would strongly consider, which is to say I would create a default static route on each one of these spokes. I would not put a dynamic routing protocol on there and just say, hey, you know what? Every packet that we send out of here, send it to that hub. And that's where a static route really can come in handy. Again, a couple of good places are particularly helpful in any of these circumstances. If your spoke routers are not exactly top of the line, what if the routing tables, like I said, what if they're huge? What if you have a routing table on a router that's not particularly strong and it's 50, it's got 50 separate entries in it? Also, it does save on bandwidth because, as I mentioned, static routes don't use any bandwidth. It's a static route where no matter what routing protocol we run on the hub and spoke, we're going to have some kind of overhead. You're either going to have regular routing updates that you probably don't need, or you're going to have some kind of hello. So there's always some kind of cost with a dynamic routing protocol. Hub and spoke network like this, I could see, again, it depends on the exact scenario. But generally speaking, with hub and spoke networks, you can get away with putting a default static route on spokes, and you are gold. Speaking of routing protocols, let's talk about RIP here for a moment and distance vector routing IGPs as a whole. This is a big change for those of you who were on the previous CCNA track 64802, because RIP has 99% been dropped from the CCNA. There's no configuration of it in Cisco Press's books. There's hardly even a mention. But I am going to mention RIP a little bit here because you need something to compare it to, because we're going straight to OSPF here. We're pretty much skipping, RIP version 1 and 2 in the mass and all that stuff. And if you have never seen RIP in your life, no worries. Like I said, I'm going to give you 5 or 10 minutes here, and that's just about all we're going to talk about it. But you need to see some of the behaviors that link state protocols have in order to understand and comprehend how fantastic link state protocols are, which OSPF is one of those. The main distance vector protocol, and I would go as far as to say the only one you're going to run into in production networks today, would be RIP, the Routing Information Protocol. We used to have IGRP, but that's long gone, years and years. And the only reason I mention it is that's where EIGRP comes from, because EIGRP is going to be all over your exams, and that is the enhanced version of EIGRP. That's actually what the E stands for. So there was actually an original IGRP, but boy was it dumb. You couldn't tell it anything. But at the time it was fine, but it would not work for us today. So RIP is really the last distance vector interior gateway protocol that we have. Now again, you're not responsible for configuring RIP on your CCENT exam. I feel kind of funny not doing it because it's always been on there. But you should know a little bit about it also to be able to compare them to link state protocols. And I want to discuss with you 2 distance vector protocol behaviors that you will not find in link state protocols: split horizon and route poisoning. And the real reason I want to mention these is because I want to introduce you to the term routing loops. First off, please note we're talking about routing loops here. When we talked about spanning tree protocol earlier, and when we talk about it a lot more in the CCNA portion of the course, that is a switching loop prevention protocol. That's layer 2, this is layer 3, and never the twain shall meet. Now, a routing loop occurs when an overall path to a destination in the packet enters a loop where the packet is routed basically in an unending circle. And actually, I'm going to make a note of this as soon as I'm done here. I have a longer video on YouTube. It's actually called Routing Loops in the Wild, because lots of books talk about routing loops, but they never really show you how they form, or videos do the same thing. I've got a free video on YouTube that'll show you how to do that. And I'll either put a link to it here, or I will just load it into the course. Now, because I want you to see what one looks like, because you can't troubleshoot it unless you can recognize it. Now, if you're wondering, hey, why don't link state protocols have loop prevention behaviors, Chris, if this is so important? Well, stick around, because you are going to see that in the OSPF section. Split horizon and route poisoning. Split horizon is a simple but powerful loop avoidance feature. The rule of split horizon simply states that a route can't be advertised out the same interface upon which the advertisement for that same network was originally received. So if we're running a link state protocol and a route is learned about and an update comes in on Ethernet 0, and then because of split horizon, that same route could not be advertised back out Ethernet 0, because that can lead to routing loops. Simple enough. Now, so is the concept of route poisoning. Route poisoning occurs when a route becomes unavailable. Now, you would think that a distance vector routing protocol would simply stop advertising a route when it becomes unavailable, right? I mean, that's the first thing I thought when I learned about route poisoning years ago when I started my studies. Like, why doesn't it just stop advertising it? Well, that's one of the problems with the distance vector protocol, and it's one of the reasons that they're being phased out of these exams. Because what happens with route poisoning, the router with the failed route continues to advertise the metric, but with a metric indicating that the route is unreachable. And with RIP, that means advertising the route with a metric of 16, which RIP considers an unreachable route. Now, upon receipt of the advertisement containing the metric unreachable, the downstream routers remove the network from their routing tables, and they will no longer advertise that route. Now, this is the kind of thing that used to make me slam my head on my desk 10 years ago, which is why I have this big dent in my head today, is because I would read this and just say, what? Yeah, that doesn't make any sense to me because, and I hope you'll agree with me, the simplest thing would be just stop advertising the route. Why are you going through this whole thing of let's poison the route and mark it unreachable and send routing updates out that say it's unreachable? Well, this is one of the problems with with distance vector protocols and RIP in particular. They don't do what we call convergence very quickly. In today's networks, when there's a change, when a network is lost, when a network is learned, we want that news to go out as quickly and efficiently as possible to the rest of the network. Distance vector protocols do a horrendous job at doing this. If you've ever worked one even in a lab environment, when you take a network out or when you add one on, especially when you take one out, it's really, really slow in having the entire network notified and agreed that, hey, a change has taken place here. So that's another reason I wanted to mention these two features. I doubt you see any questions about split horizon or route poisoning, but the reason they existed is because RIP just converged so slowly. I mean, it was a nightmare. You'd be sitting there clearing your routing tables trying to get it caught up, and that's in a lab environment, so you can imagine what it was like in a production network. And I just wanted to show you here another debug IP RIP. And here's the output of debug IP RIP when a route is being poisoned. And you can see right here the metric of 16. I didn't do a very good job of drawing a box around it, but you can still see it. It has a metric of 16. This leads to another reason that you don't see distance vector routing protocols around very much anymore, and that's that awful metric. I kid you not, this sounds like a joke. But RIP's metric is literally called hop count. It's how many hippity hops there are from point A to point B. I kid you not, that's what it is. And that was fine at one point, but it's not fine today because you can have so many different speeds on paths. You know, if you have one path that's running at fast Ethernet speed and another one's running at gig Ethernet speed and another one's just running at regular Ethernet speed, RIP sees all three of those links as being the same. One hop. I kid you not. So that's another reason that you really don't see RIP around much anymore and why they've pretty much phased it out of the exams. The big reasons, it converges very slowly and this with the unreachable metric, and also simply that it just sees every link as being the same. The hop count metric is just not a good way to go about things. And I mentioned here RIP uses what we call the Bellman-Ford algorithm, which does result in RIP using hop count as its sole metric. Again, RIP doesn't consider the bandwidth or the speed of a path, it just counts hops. Not very scientific and not something that we want to use in today's network. So again, just some quick review here of the issues and why we don't see RIP around much anymore. Slow convergence, inaccurate metrics, and believe it or not, on top of everything I've told you in the last few minutes, there is actually more. Two versions of RIP exist, one of which did not support subnet masking and used broadcast instead of multicast. And I'm not kidding, RIP sends out a full routing table every 30 seconds, regardless of whether there's even been a change in the network. This is a huge waste of router resources and bandwidth, because as I've said in previous classes when I would teach RIP, if your network is changing every 30 seconds, you should not be in this class. you should be troubleshooting your network. You should not be here. So these are the main reasons that you will not see distance vector routing protocols around much. And it also gives you a good background to compare link state protocols such as OSPF. And EIGRP is not a pure link state protocol, but it's real close. We'll talk about that when we get to EIGRP. But speaking of those protocols, let's head there next and talk about OSPF. I'll see you on the next set of vids.